Hi, I am Madam Rosmaya. In this video, we are going to discuss about power in an AC circuit. The AC circuit that we are going to discuss consists only either of a resistor or capacitor or inductor. Recall to what we have learned before in this YouTube channel about the phase relationship between current and voltage. So for AC through a resistor, I and V are in phase. For AC through an inductor, V leads I by pi per 2 radians. And for AC through a capacitor, I leads V by pi per 2 radians. Okay, recall to what we have learned in secondary school. In a DC circuit, the power consumed is simply the product of the DC voltage times the DC current, given in watts. From formula power equals to IV, we can get P equals to V squared per R and P equals to I squared per R by substituting V equals to IR into the equation here. Example, in this circuit, if current is 2 ampere and voltage supply is 12 volt and resistance is 6 ohm, so using the three equations given here, all we get same answer, 24 watt. So this 24 watt means the power consumed by the resistor is 24 watt. In DC circuit, the voltage and currents are generally constant. That is not varying with time, as there is no sinusoidal form, just a straight line here. However, in an AC circuit, the instantaneous values of voltage and current always changing, shown by the sine graph here. And therefore power are constantly changing, being influenced by the supply. So we cannot calculate the power in AC circuits in the same manner as we can in DC circuit. So we discuss first on the AC through resistor. So using power equals to I squared R, substitute I equals to I naught sine omega t and omega is 2 pi ft into the equation here and expand the bracket here, we get P equals to I naught squared R sine squared 2 pi ft. And we plot the graph P against T. So we get a sinusoidal shape of graph because of the sine squared here. So the sine graph is plotted on the positive side of the graph. Amplitude is given by I naught squared R. Okay, now we plot V against T and I against T in the same PT graph to compare or to observe the relationship between the power I naught and V naught. So from what we've observed before in this YouTube channel. So we get this graph where I and V are in the same phase. So during the positive half cycle, I and V are positive, as positive times positive, so we get power positive. So during the negative half cycle here, I and V are negative, so resulting in the power being positive, because negative times negative is positive. So for area under the graph, is a positive power, so means that electrical power is consumed all the time that current is flowing through the resistor. And the mean power is equals to half I naught squared R. So we have discussed this in the YouTube channel here, where mean power equals to half I naught squared R for the power of a resistor in AC circuit. So we've done AC through a resistor. The power we get I naught squared R sine squared 2 pi ft, and the mean power is half I naught squared R. So next we discuss power for the capacitor in AC circuit. So we use P equals to IV formula, and from the previous lesson, V is V naught sine omega t, and I we get I naught cos omega t. Okay, from the YouTube channel here, we get these two equations and substitute into I and V here. So we get P equals to I naught V naught sine omega t cos omega t. And simplify the equation using double angle formulas. Sine 2 theta equals to 2 sine theta cos theta. So therefore sine omega t cos omega t becomes half sine 2 omega t. And bring half to the front becomes P equals to half I naught V naught sine 2 omega t. So the graph we get is a sinusoidal shape because sine 2 omega t, so the frequency become double. Compare with the VT graph, so we plot VT graph and IT graph in the same graph. Just now V equals to V naught sine omega t and I equals to I naught cos omega t, where I lead V by pi per 2 radian. So in the first cycle, first quarter cycle, both V and I are positive. So therefore power also positive. So for the second quarter cycle, V stays positive and I negative. So therefore P is negative. And in the third quadrant, both I and V are negative. So we get P positive. And finally, the fourth quadrant, I is positive, V is negative, so resulting P power negative. So as a result, the power wave is thus a series of identical positive and negative pulses. And the average value over half cycle of voltage is 0. And as a result, the mean power for the whole for the capacitor is equals to 0. So no average power, no heating will occur, and no power is lost. And also note that its frequency is twice the frequency of the voltage. So for one complete cycle, here voltage compared with the voltage graph, VT graph, so we have one complete wave. For power, we have two complete wave for one cycle. So that's why the frequency of the power is twice the frequency of the voltage. So for area under the graph, for positive power, indicates that power is supplied by the circuit to charge the capacitor. And when the capacitor is discharging, and thus supplies the energy stored in it back to the circuit, so the power has a negative value, shown by the area colored, green colored here. So we've done power for a capacitor. We get P equals to half I naught V naught sine 2 omega t, and the mean power is 0. Okay, next we discuss AC through inductor. So the power we use equals to IV, and voltage is given by V naught sine omega t. So this is initial voltage we discussed in the previous YouTube channel before here. And we get I equals to negative I naught cos omega t. And we substitute into the equation. And we get P equals to negative I naught V naught cos omega t sine omega t. And using a double angle formula, sine 2 theta equals to 2 sine theta cos theta. So we get cos omega t sine omega t equals to half sine 2 omega t. Okay, bring half to the front, become negative half I naught V naught sine 2 omega t. So now we plot the graph P against T graph. For sine 2 omega t, so that's mean we have double frequency, same as before, but this time because negative, so we plot oppositely from the previous power, and negative side. Start with negative side because negative here. So this is the graph P equals to negative half I naught V naught sine 2 omega t. So we plot V against T and I against T on the same graph. Okay, as we have discussed here in the YouTube channel here. So we get this graph where V lead I by pi per 2 radian. Okay, so this is the graph for AC inductor circuit shown the voltage leading current by pi per 2 radian. So in the first quarter cycle, V stays positive, I negative, so therefore we get P negative. In the second quarter cycle, both V and I are positive, so power we get positive. In the third quadrant, I is positive, V is negative, so resulting P being negative. And in the fourth quadrant, both I and V are negative, so P is positive. So we get the power wave is thus a series of identical positive and negative pulses. And the average value over an half cycle here is also 0. And therefore, the mean power is equals to 0. So no average power, no heating power will occur, and no power is lost. And same as before, the frequency of the power is twice the frequency of the voltage. As we can see here, for one complete cycle, we have 2 complete wave for power and 1 complete wave for voltage. So that's why frequency of power is twice the frequency of voltage. So the area under the graph colored by yellow color here means the positive power indicates that the coil is consuming electrical energy from the supply. So energy supplied to inductor by AC supply. And for the negative power here, area colored green colored, the negative power indicates that the coil is returning the stored electrical energy back to the supply. So energy returned by inductor to AC supply. So no real power is used up since the power alternately flows to and from the source. This means that the total power taken by a pure inductor over one full cycle is 0. So we've done AC through inductor. We get power equals to negative half I naught V naught sine 2 omega t, and the mean power also 0. Okay, that's all for the discussion today. Thank you for listening and watching.